And so I'm going to give a brief overview of what we're trying to accomplish here. This is going to be repetitive for the attendees, but I want to run this with the new panelists because some of them were not there this morning, so that they can get in the mood of what NGenE is. Next Generation Electrochemistry is funded by the National Science Foundation. They've been funding us since 2016 very generously, and they're still funding us. ECS is a sponsor, and this live broadcast is being recorded, so it will be posted to the ECS YouTube channel after NGenE is done. And this is run by the University of Illinois Chicago. My name is Jordi Cabana, and I'm at the Department of Chemistry at UIC, and I'm the director of the program. Thomas Alan is also in the call, and he's the one turning all the wheels so that they spin properly. And we have, and then George Crabtree at UIC is also the supporting director. Normally, this program runs for a week in the summer, and it's in person or face to face. Because of the COVID pandemic, we had to cancel the physical version, but we still wanted to have something going on. So we decided to run a condensed version that is only online, live, and open for everybody, with 4 panel discussions. This morning we had one on energy storage. That's the one that we didn't manage to live stream, but will be posted to the ECS website. We're in panel 2 on integrating computational and experimental approaches. And tomorrow we have 2 more panels, one on emerging topics at the water energy nexus, and one on another topic that is gaining a lot of attention recently, which is kind of having a major comeback, which is organic electrochemistry. And the first one will run at 10 Chicago time. The second one will run at 1 p.m. Chicago time. If you are attending this call in the Zoom version, you were given the details and you want to attend the other panels and you don't have the information, contact Thomas. You have his address because he's been emailed you. So this panel, just like the panel this morning, is meant to be a discussion, and the panelists drive the discussion. They're eminent experts in the field that we're covering. So they're the best people to give an overview of where the field is. Each panelist will give a 5-minute opening statement. They'll all show slides. And this opening statement, the challenge that I gave to them is to present fundamental questions on the topic at hand, on the topic of this panel. We want it to be connected to electrochemistry as a science more than any specific application. After that, we will have discussion. The discussion is driven by the panelists. I will be moderating it, but there's around 40 attendees who are students and postdocs in the country selected. And they have an opportunity to chime in and throw questions at the panelists. And this worked really well this morning. We are live stream on YouTube, and hopefully the hundreds of people that tried this morning are persevering and trying again. And we will run for about 90 minutes. We went a little over this morning. The 4 panelists were very generous with their time because we also had a bit of an issue starting early. So same here. The plan is to run until 2:30 p.m. Chicago time. If we go over, we might go over depending on how the discussion is going. For the NGenE faculty, my request, and the request that I made to you by email last week, is that you try to focus on presenting topics that are at the frontiers, not what we've done, but what we cannot yet do and we would like to do. It's okay to be controversial. There were a couple of statements made this morning that led to a bit of a back and forth, very collegiate. So as long as it's collegiate, controversy is good. This is an opportunity that you have to reach a really large number of young scientists that are, let's face it, going to be our replacements. And so this is your opportunity to have a legacy beyond your group by shaping the things that they want to think about that you think are important. So share your wisdom, how you go about thinking critically, and let's try to keep a focus on basic science and not go too much into aspects of application. For the attendees, for those of you in the Zoom call, again, get involved. This morning, I told you to post on the chat that you're interested in asking a question. I changed that. Actually post the question on the chat. Your mics are disabled by default, but we'll enable them so you can ask in person. But we had a couple of issues with a couple of people where the mic didn't seem to be working. And so we want to be able to keep going. And so we'll give you a minute or two to see if you can sort that out on your end. Otherwise, I'll just read the question and at least you can get an answer. And if then the mic works for you and you want to ask a follow-up, post it again in the chat and I'll give you the floor. Don't be afraid to challenge the faculty. They're here for that. They know that you are here to ask difficult questions. And so, you know, go at it, absorb as much as you can, and use this, think of this as a way to figure out where you're going to go with your own career. You know, you may decide that after this, electrochemistry is too depressing and you want to go into another field. That's fine. Hopefully that's not the case, and you get ideas on things that you want to do afterward when it comes to where you want to take your career. With that, I'll stop. The agreement was to alternate experimentalists and computational scientists. And so Mike Toney will be going first. Mike is at Slack, and he's moving to University of Colorado in August. Andy Gewirth is at University of Illinois Chicago. He'll be third because he's also an experimentalist. Don Siegel will be second. He's a computational scientist at the University of Michigan. And then last but not least, certainly, Perla Balbuena at Texas A&M, who also does computation. So you'll see that there's a 50-50 balance because I don't count. You know, I'm only here to moderate. I don't say anything. Okay, so with those introductions, Mike, the floor is yours. 5 minutes would be great. I won't hound you if you go a minute or two over, but let's keep it moving.
There we go. Yeah, I'd actually unmuted myself. No, I'm not accidentally.
That's
so
good.
hopefully everyone can see this. What happened to this slideshow? Sorry, I seem to have lost the slideshow mode. There we go. Okay, great. So I'm going to talk kind of about two different, somewhat different aspects relating theory and computation. And I'll start with interfaces, and because this is, because I'm an experimentalist, this will be a little bit experiment heavy. So I think kind of by definition, anytime one talks about interfaces, you have to give this quote by Pauli. So the fact is that understanding and characterizing processes that happen at interfaces are hard. And that's basically due to kind of two reasons. Oops, it didn't quite work. Kind of written down here. One relates to sensitivity. And so this really is a matter of how many atoms one typically is probing in a given measurement. So kind of surface densities, and I've illustrated that kind of down over here, are somewhere on the order of 10 to the 15 atoms per centimeter squared. And if you can kind of compare that to something that you might hold in your hand, bulk, say crystal of some size, it's going to have somewhere on the order of 10 to the 20 or 10 to the 22 atoms. So the nature of the surface, by definition, means you have to kind of conduct very, very sensitive measurements. The other one is kind of illustrated in this image here. So this shows basically an interface that is relevant to the discussion at hand. And so that one that has to do with electrochemistry. So we have an electrode that's sitting down here. We have a bulk, in this case, liquid electrolyte that's sitting on top of that. And then we have this interfacial region that's kind of illustrated in blue that is labeled layered electrolyte. So the selectivity part of it gets to the fact that our interface here is in some level buried between this liquid electrolyte here and the electrode that sits down here. And so that means that one has to be not only sensitive, but also selective to measuring the interface. So experimentally, that's challenging. It's actually maybe a little bit easier theoretically. So let's just illustrate that over here. So these are some results that have been done by Oleg Bordin at the Army Research Lab, and partly illustrated over here for kind of this conventional electrolyte that one would see in a battery, and hopefully was mentioned a little bit earlier, kind of in the discussion this morning. So this is kind of a schematic. Here's the electrode sits out here. Here are the various carbonate molecules that are adjacent to that. You can see the layers. This is the anion, and the cation is lithium, which is shown here in these little purple regions here. What I'm showing over here basically is one thing you can get out of this, which is basically a density profile. So it's the number of molecules away from the surface. The surface would kind of sit somewhere in here. And so this is a result of kind of a simulation. So, and the reason that this matters in terms of electrochemistry is basically any process that you have that's going to happen at the interface has to kind of happen from these molecules. So I'm not showing reactivity in that. Hopefully Perla or someone will discuss that a little bit. But any reaction that happens at this interface basically has to start with these molecules. So understanding this and understanding that the reactivity is really important. So as I mentioned, the theorists can do a very good job of predicting this, can argue about their accuracy. Since Jordy asked us to be controversial, I think sometimes accuracies may be a little bit oversold. You can also get insight into the orientation. So this gives you some idea of what the orientation of the various carbonate molecules are. So the theorists can do this well. It's actually very hard to do this from kind of experiment. You basically don't know how to get this kind of information. You can get kind of averaged information, so averaging kind of throughout the molecules, and these are some of the results shown in this paper, where basically we have a substrate that sits here. The blue is the simulation, and the darker lines are actually the data. So we can actually now make a direct comparison between what's predicted in the experiment and what's predicted in the simulation and actually what's measured in the experiment. And so this actually looks pretty good. And we declared that this was victory. But the reality is we don't get molecular level insight into this. It's some average quantity, and we don't get anything about dynamics, the point I'll return to in the next slide. So I think one of the challenges, at least from the experimental side, is how do we develop kind of these higher fidelity interfacial probes? And this has been a challenge to the experimental community kind of for many, many decades. But hopefully over the next, for the young people in the audience, some progress can be made over the next number of decades. So the other part, and I expect that some of the other faculty to discuss this as well, relates to connecting time and length scales. And so now I'm moving kind of into the dynamics regime where time actually matters, because that's of course relevant in electrochemistry in terms of charge and mass transfer, as well as ion transport. And I've written down some numbers that are meant to be guides, don't take these literally. But typically simulations kind of are limited to a few, maybe tens of nanometers in terms of length scales, and reasonably short time scales, picoseconds to nanoseconds. Whereas experiments now, and again, this is meant to be a gross generalization, so details, this will be not true in all cases. Experiments tend to be nanometer plus time of length scales, and typically microseconds are the best we can do. Not always true, but largely to the case. So here's an example, right, where we might imagine purple being lithium doing a hop as it diffuses through this V2O5 lattice. So this is actually simulation. The simulation can do this with what is believed to be high fidelity. They can calculate the energy barriers of lithium moves from here over there. The atoms in the V2O5 will then go ahead and move apart as the lithium jumps. We don't know how to measure this. This is a challenge, again, from the experimental side. But we can do measurements at much longer length scales and much longer time scales. So this kind of illustrates that. So on the top, I'm plotting length. So this is small, this is big. On the y-axis, it's time. So this is fast, and this is fast, and this is somewhat slower. These processes I've illustrated over here. So they're going to be in reasonably small time scales. This is typically a few angstroms, and short times typically for this process somewhat on the order of picoseconds. We can't measure this. We can, however, measure these longer timescale processes that are kind of made up of these very short and fast atomic hop type processes. These are going to be, as stated down here, somewhere in the microsecond regime and somewhere over typically many nanometers. So the challenge then becomes basically connecting these. How do we take experiments in these slower timescales and push it down into faster timescales, and how do we take the simulation results and push them down to things that are more relevant from the experiment side? So this, at least to my mind, is one of the bigger challenges in the field in terms of connecting experiments and what experiments can directly measure with simulations and what simulations can directly predict. And this is just another example of that for those of you who care about electrolytes. This particular case is a water and salt electrolyte, which hopefully you heard discussed earlier this morning and is a topic of considerable interest. Okay, so that's kind of all I have to say. So why don't I go ahead and turn it over to who's ever next. Oh, I have to stop.
Thank you. So you can stop your and then we'll do some discussion.
Okay, hello. Can everyone see my screen?
We're good.
Yep.
Okay, great. Okay, so I'm Don Siegel. I'm from the University of Michigan, and let me just start with a quick bio. My background is in physics. And after completing my PhD, which was from the University of Illinois, I spent some time working as a postdoc at national laboratories. Then I had a 4-year stint in industry at Ford Motor Company before I joined the University of Michigan. I guess it was 11 years ago now in 2009. So I'm in mechanical engineering, but I'm basically a computational material scientist. And we tend to focus basically on modeling materials at the atomic scale. And I think you'll hear quite a bit more about this from Professor Balbuena in her introductory remarks. So I started off with a question about why one would want to use computation. And I think it's simple enough to break it down into 2 different categories. I hope I don't offend anyone with this simplicity, but my world basically divides into trying to understand processes that are happening at the atomic scale. So that's the left side of this diagram. And this is an opportunity for collaboration with experimentalists as well. You just heard Mike Toney mention that there's this typical regime of, say, time and length scale, which is often well suited by experiments, and a different set of conditions which are suitable for simulation. And so one trick is to try and get those non-overlapping set of conditions to match up and learn something useful. So I'd say that computation started out focusing on the left side, and most of the work done today in electrochemistry, at least simulation-wise, is still trying to understand and characterize materials. So there are many things one can do with computation that mimic, for example, what can be measured experimentally. And Mike just showed you a pair distribution function that can be measured experimentally and predicted. So there's an opportunity for direct overlap in some cases, but not in all. And so looking to the future, we still don't want to give up. I mean, we have not addressed all of the characterization issues, and we don't understand everything that atoms do in an electrochemical context. And so some of the challenges are, again, just to try and figure out how do we simulate these electrochemical processes at say, time and length scales that are meaningful. Mike mentioned that on the simulation side, we are typically limited to very short time scales, say maybe a nanosecond or less. And same thing on the length side of things, a nanometer is a good ballpark for an atomic scale simulation. But on top of that, there are other conditions we'd like to take into account, for example, temperature, pressure, or the presence of an electric field. And to some extent, all of these can be factored in, not necessarily at the same time and with accuracy that we're happy with. So there's still quite a bit, I'd say, of developmental work to be done on the computational side to make our computational probes more accurate and useful. And then moving on to the right, looking to the future, in the past, I don't know, 5 or 10 years or so, it's become possible to make basically to transition computation away from, I'd say, only a tool for understanding, but into a tool that can make predictions and help us discover new materials. And this is exciting when it can be done. It can't be done in all cases. Sometimes the things we need to calculate are too expensive, or the number of systems we would need to explore to learn something are just too numerous. But I expect that we'll see more of this as time goes on. This is also another great way to interact with experimentalists, because often experimentalists are happy when you give them things that show some promise, maybe are thermodynamically interesting, have a high capacity for maybe storing lithium. But it's also really challenging because there's all sorts of things that can come up, things that we don't understand about systems that our simulations don't take into account. So I'd say there's a certain amount of humility that has to go along with discovery and prediction. We don't necessarily know everything, and it's possible that we can make mistakes and be wrong. So, I guess with great power comes great responsibility. That's how to summarize the discovery side of things. So, I know Jordy said, we're not focused on applications, or if you feel bored with electrochemistry. I personally don't think that's possible in my case, because the applications are so enticing. And one of them that I'll just mention here is energy storage, which largely can rely on electrochemical processes. And so as you see in this diagram, electrochemistry and in particular batteries play a role in many different technologies that could have some benefits, some real benefits for society. And then finally, I'm going to just wrap up on this third slide and say that one of the nice things about computation is that you can use it to study many different types of processes. So here we're talking about electrochemistry, but thermodynamics, kinetic properties, even electronic structure, things like band gaps can be probed with the right computational technique. And so, and there's also a range of different techniques that span from, say, the atomic scale, where we prescribe an interaction between atoms, say, for example, molecular dynamics, but we also dig very carefully into how the electrons are behaving, and we call these quantum mechanical or density functional theory calculations. So there's a range of tools available in the computational toolbox that makes computation, I think, a really powerful tool. So let me stop there.
Thank you, Don.
Okay.
Andy, you're up.
All right. All right. So thank you, Jordy, for arranging this. And now I'm supposed to be hitting buttons here, but it is not. Oh, there we go. All right. So I'd like to talk. So thank you, Jordy, for arranging this and for the introduction. I'm at the University of Illinois, Urbana-Champaign, not Chicago. And I've had a sort of eclectic background, just a little bit. I started out as a what we called physical bioinorganic chemist. And at that point in time, what we did was we did spectroscopy, and we measured transitions. And then we used calculations to try to understand what we measured. In those days, and I'm ancient, we used something called X-alpha scattered wave calculations, which featured the so-called very descriptive muffin tin potential. Now I think superseded slightly. And we were able to calculate one electron energy levels and look at energy differences between one electron energy levels and sort of model the experiment. And then when we got a match, we would then look at the ground state. We'd have a less sophisticated computer graphics program, which would then spit out these what the ground state looked like, and then we got published in a high impact journal. So when I got to the University of Illinois, my colleagues, I realized gas-phase colleagues makes it look like they're lightweights, and they're not, right? My colleagues were using mantras like this one right here: theory guides, experiment decides. And I thought that was very interesting, but I wasn't really clear about how that would translate into the work that I actually did. And in fact, the reality was that we would make measurements on random topics, energy storage, electrocatalysis, things like that. And then we would run to our friends, the theoreticians, and say, what does this mean? Please tell us what this means. And oh, by the way, provide a full color picture so we can get into a high impact journal. And so I'm being a little facetious here, but and so here's an example of something that I thought was, successful. This is collaborative work I did with Maria Chan and Jeff Greeley when Jeff was at Argonne. And so we did a Raman measurement, right? And we're looking at the onset potential for lithiation in a solid state material. This is a silicon material. And you can see that when you change the doping level, you change the onset potential for this. So this turned out to be something that was really good for the theoreticians to be able to look at, because first there was a thermodynamic quantity that we were looking at, the onset potential, or the potential that lithiation started. And then second, it didn't involve complicated things like interfaces that Mike alluded to, or things like that. And so Maria and Jeff did calculations, and the calculations basically showed what the physical insight and the measurement predicted, which is that, P-type would be easier to lithiate than the N-type. And we got some, sort of quantitation there and published it. It actually didn't go into a high impact journal, but that's okay, right? So that worked out quite well. We measured a thermodynamic quantity. The experiment, the calculations reproduced this thermodynamic quantity to some level, and helped explain what we were seeing experimentally. That worked out really well. So now we move into the modern area right here, and things turn out to be somewhat more complicated. One of the most complicated ones, I think, is the first point right here, and that is what I typically measure as an electrochemist is a rate. I measure current, and what the calculations provide mostly, and particularly popular ones that that I can download, and even someone like me can use, like VASP or related ones, is they provide energies. And of course, these two are related, but you actually need to measure, or you need to provide a rate, not an energy, right? Second, I think, as Mike alluded to, a complicated interface is not yet fully described by calculations. And I'm just sort of listing some topics right here where we've had sort of butted heads with people, with theoreticians. And again, I'm saying these things slightly to be a little provocative right here, and Perla will, of course, jump on me. But for example, you have an alloy surface that's 1% in the alloy, right? And someone says, why don't you do a calculation to, describe the rate of CO2 reduction in the presence of this alloy? It's faster, substantially faster, right? And they go like, well, the unit cell would be, 8 zillion times, 8 zillion. And so that's a problem. You typically put in minority components. For example, in copper electrodeposition, you have various trace amounts of additives that completely change the way that copper is deposited. These seem to be very difficult to model. You have charge transfer in the presence of substantial heterogeneity, and interfaces that are only partially conductive may have other kinds of components available, oxides, things like that. Very difficult to model or to understand from both experimental and theoretical perspectives. In other areas, for example, non-precious metal oxygen reduction reaction chemistry, there are a number of calculations which purport to explain experimental facts in the absence of full or even partial characterization of what the active site looks like. And you just have to sort of throw up your hands about that. And then charge transfer in the presence of chemical or electrochemical heterogeneity, and in the battery world, magnesium or calcium electrodeposition would be examples of this kind of thing. We have a through the glass darkly experimental understanding, and many times that understanding doesn't seem to overlap very well with what theory or calculations are providing. So Don mentioned something that I think I think is very interesting and still challenging, and that is what an experimentalist would like. I mean, what I would really like from Don and Perla and my colleagues would be someone to say, if you made this alloy, you would have the best CO2 reduction reaction catalyst on the planet. Or if you tailored this interface in the following way, lithium conductivity would be, very, very high. And that would be a prediction, and then we could go do it. And there have been some examples there of people trying to do this. For example, there were some calculations about various alloys for the oxygen reduction reaction, platinum alloys for the oxygen reduction reaction. And those turned out to be less relevant to, you know, sort of the real experiments, and were difficult to synthesize. There was a test, and it was okay, but you know, needed some work. And that sort of leads to the last part right here, and that is, you know, the use of machine learning or AI. And I guess I'd be interested in hearing what our other panelists have to say about this. And is this really something that's going to change things? Should we all be looking into this? Can AI or machine learning tell me that my present research directions are hopeless and that I should be going into another area? Or is it perhaps a mix of something else? So that's what I have, and I'll be interested to participate in the discussion. Thank you.
Okay, thank you, Andy. Perla, the floor is yours.
Okay, hello, thank you very much for letting me share my thoughts about these interesting topics. My name is Perla Balbuena, and I'm a professor at Texas A&M. So what I did here is to think about the questions that Jordi sent to us with respect to this panel, and see what would be my answers with that before entering into the discussion with all of you, that I'm much looking forward to it. So the first question is, what kind of experimental inputs would models benefit from? And is connected to the slide that was just shown by Andrew, actually, as you will see. So my short answer would be, we need all the input that can help us to define our models better. So then my next step is to explain to you what I mean by defining the model. So by defining the model, I mean going from the problem to exactly build a physical model that allow me to do the computation. So it's actually the one in the center of these three steps, the one that is important, is defining the physical model. And for that, I still need experiments. So maybe in the future, the models and the computers and everything will be so advanced that we won't need this, but it's evidently needed right now. So I will give some examples. We need characterization experiments. And that was one of the points that Andrew made. So we need to understand what type of surface we have, what kind of surface chemistry, if there are defects, what are the concentration of those defects. The best that we know, the most that we know about the problem we are trying to model, the better the model will be. Then the next thing is we need to know about synthesis and processing of materials. For example, well, there are many materials that are now being proposed or used for these beyond lithium-ion chemistries. For example, carbon-sulfur composites are really complex systems. And it depends a lot of how you make the material, how you make the synthesis, how you process them, what are the properties that you are going to have in your device. So that is also an important knowledge that we need. And synthesis and processing of assembled devices, for example, batteries or electrodes, individual electrodes made of individual particles, right? And then other example could be phase transformations, like things that happen at the metal oxide cathode that everybody is familiar with, probably most people are familiar with, these phase changes that happen in the metal oxides and that modify interfacial phenomena at the interface between the electrode and the electrolyte, and that we are trying to model. But in order to model the interfacial phenomena, we need to know what's going on with the actual material. So the next question is, how could experiments and characterization be best guided by computations? Well, and this is, what feedback can we provide to experiment? And that was mentioned by Don, and really there are a lot of things that are being done right now, but there is a lot that we need to improve in order to give a better picture of the actual phenomenon. So I listed here some of the things that people publish or that are being reported, like, and topics that I think need a lot more work. Let me see if I can use my laser pointer. Are, for example, nucleation, evolution, degradation, all these things that happen in our electrochemical systems continuously, and that even though we are trying to study them, we need much better improvement in our methods in order to get a better picture. Others are stability of materials, for example, the knowing if our materials are within the electrochemical windows, thermodynamic diagrams. These are sometimes very useful as well to characterize our materials that we are going to use for electrodes or electrolytes. Ionic transport mechanisms, and this includes things that that happen once in a while and that are very difficult to capture with regular computational methods. Reaction mechanisms, of course, everybody talks about interfaces, that's crucial in electrochemistry. Electronic structure, molecular and materials design, that is what we aim to do, actually. And then this one is, I think, is a point that I would like to have your input as well, because there are properties or variables that are being manipulated at the fabrication level. For example, let's say pressure, that modify the structure of our materials. So incorporating those into our computations is also really important. Helping identifying experimental spectra, and then one aspect that one of you mentioned, I think it was Mike, who mentioned about ultra-fast phenomena. So the discrepancy between the different scales that are being addressed by theory or by experiments. So I think we need to take advantage of the fact that our computations allow us to go into a regime where experiments cannot, because probably things that happen at that time scale or length scale are definitely affecting what happened next. And to the point of machine learning, yeah, I want to mention this. The last question was, can computational analysis directly be integrated with data analysis from experiments? And I want to bring this paper by Frenkel. It's a catalysis paper that is characterizing a phase transition in iron induced by temperature. So iron goes from one phase to another driven by temperature change. And what they did is to combine data from X-ray absorption fine structure spectroscopy with classical molecular dynamic simulations, and all of this is data that is provided to a neural network algorithm, and this neural network algorithm is able to train by being trained by this information, and then produce at the end the radial distribution functions that that correspond to the transformation taking place in this in situ experiment. So this is, in my opinion, very nice, and we definitely would like to have more of this in electrochemistry. Well, and finally, probably I'm over with my time. So finally, I just want to list what I consider fundamental questions or challenges in our field. Crosstalk issues in batteries, particularly with new chemistries. Recognize the role of thermodynamic versus kinetics in certain electrochemical processes. Degradation phenomena, I already mentioned that. Those are crucial. Those will lead to our to prediction of lifetimes that are not yet available and that we would like to be able to do. There are computational methods that needs to be improved, and this is just one of them. For example, systems that require higher electron correlation, like oxides, and need better theoretical methods. I already mentioned synthesis, the role of synthesis, and finally, data science integrating computation and experiment. I think that could also lead into new models. I mean, going beyond correlations that can be obtained from what we observe. And probably the machine learning is able to, you know, process much more than our brains can in similar times, right? In similar time frames. So, so we expect from this to be able to process these complex phenomena and get maybe better models for our systems. Okay, so with this, I just stop to go into the actual discussions in the panel.
Okay, thank you, Perla. So now it's we'll spend the rest of the panel having a discussion. I've been seeing questions from the attendees, so I am going to start throwing some of those at you. You've touched on machine learning, and we had a question from Yumin that had to do with machine learning. Let me make sure that I get the right name. Yeah. Okay. So Yumin, I'm gonna give you the floor, and you can ask the question. Oh, you already got it. Okay. Go ahead and ask the question that you were asking about machine learning.
Okay, thank you. Can everyone hear me? I think
yes.
so. So in the last panel, George mentioned that he mentioned the battery design approach from bottom up, basically from atom to atom and to the system level. So I think this is really important. It's also this idea really resonates a lot with me. I think we need a supply chain of simulation. So my question is, the only methodology that I think of that can make this happen is using machine learning force fields to speed up the simulation of quantum chemistry accuracy. So my first question is, so for machine learning, we need a large amount of high quality data. So what do you think the data can come from?
You mean the data for machine learning?
Yeah, the training set, basically.
Okay, the training set.
So who wants to take that on?
In the example that I show you, there were actual experimental data, but there were, or maybe you are talking about the force field, the data for the force field training. But anyways, the data could be a combination of experiments and computations.
Is that what you were asking? You mean you have the floor again, so you can follow up if you want to clarify anything.
Yeah, I think so. I have been doing some reading. I think the data, so from my understanding, data, probably the best of the data set can come from the AIMD simulation, but I think there's a drawback here. So if we actually talking about AIMD simulation data, I think AIMD is it costs a lot of resources, and I worry that it will not cover enough of the chemistry space. I don't know if there's other route that I should look at.
Like you mentioned, the AIMD can contribute data to generate force fields for the classical MD.
Is more model data what's needed for machine learning, or are there aspects, as you talked about how some of the, in the example you discussed, those were experiments. So,
yeah.
is there a limitation right now because people are, not collecting enough experiment, or, are experiments really needed for a training set? What is the crosstalk here? Go ahead, Don. You want to say something?
Yeah, I would just say, I mean, yeah, you need some data on which to train the ML, but and that can come from any source that you think is trustworthy, be it experiment or computation. Sometimes the motivation to get that data isn't so strong, right? No grad student wants to take hundreds or thousands of measurements just to parameterize someone's ML model.
Right.
So it's kind of like you got to find an excuse to get that data. Where does it come from, and does it have some intrinsic value beyond just training ML?
Are there opportunities for crowdsourcing then?
I mean, maybe robots can do this work.
I think it's the robots.
Maybe it's not interesting enough for a human to do it. But I would also, going back to the first part of the question, this design, from atoms on up. I mean, machine learning could help with that, but I don't necessarily think it's the only way to do it. One could just make composition changes to a material and hope that other things stay more or less the same, and ask, does that lead to an improvement in performance? And the other thing that's, to come back to ML for a second, what is challenging about ML is that the models only know about what they've been trained to know about. And often we want to know about materials that are exceptional, that we haven't thought about before, that aren't part of our training set or don't look anything like what's in the training set. So the issue of extrapolating, getting a machine learning algorithm to make a prediction beyond the space for where it was trained is an active area of research. And who knows, it may work in some cases, but not others.
So could I maybe,
go ahead.
Yeah, could I kind of follow up on that? So I guess this is a question to both Don and Perla, is what are the prospects for using AI and machine learning actually to discover what Perla phrased as new physics, and I think Don was alluding to as well? Just based on the fact that it only knows about what it's been trained about. So if you want to throw in something new, how do you actually do this? And what's required, what will be required in the future to kind of do this?
Mm-hmm.
Well, I mean, I would say, I mean, this is research, so we don't know the answer to that question.
Okay.
There's a trivial answer.
Right.
So if I can do a regression analysis and plot the thing I care about versus the thing I can control, I can extend that line out into whatever space, whatever composition space. But usually that's not very satisfactory, and life is not linear like that. So I would say that you can't take chemical intuition out of this process. I think an appropriate way to use ML is to inform your intuition And one thing that, I don't think gets a lot of attention is that people are quite interested in making predictions with ML, but you can also reverse that process and ask like what features that fed that model are the most important for making that prediction. So, maybe it's something as simple as electronegativity. You can use the model to find relationships that a human might not notice because the data is so complicated. And so from that, then you could infer a new direction. A human has to be involved in that process, of course. So I don't think this is there's no cookbook yet about how to discover new materials with ML. And if there was, we probably wouldn't be interested in it.
You mean, did that answer your question? Anything that you want to follow up on?
Yes, that answered my question. Thank you.
All right, Jeff, I'm gonna call on you because I do want to get to the topic of interfacing of computations and experiments. And Jeff had some very good insights in terms of the questions that he submitted up front. So you don't have to ask it in exactly the same words. Some of these things may have evolved now that they've talked a little bit. But why don't you attack that issue that you raised?
Okay, yeah, thanks, Jordy. So I'm Jeff Lowe. I'm a postdoc at Purdue University. And one of the questions that I had that was kind of touched on a little bit in some of the discussions so far is that I see a lot of high impact papers that are combining experimental and computational approaches, but it's often not effectively integrated. So for instance, you might have a primarily experimental paper and then a computational figure is, for lack of a better phrase, sort of thrown in at the end. So it's the last figure in the paper is this computational figure. And the system may or may not be consistent with the experiment. So I'm wondering, how can we improve this integration of experiment with computation so that they can really effectively complement one another?
So I will make,
Go ahead, Mike.
Okay, so, and I think someone raised this, but it would, oftentimes, and again, speaking as experimentalists and meant to be a little bit provocative, and Andy kind of touched on this, we'll go back to our theorist colleagues and ask them to explain a result. And invariably, they always come up with the right answer because they know the answer, so they're going to get it right. So, it'd be helpful for us to, and in many cases, to actually design an experiment to know what we should, to have a prediction on what we should be able to get. And actually a prediction that is actually measurable. Kind of gets back to what I touched on. And so if you can make a prediction on what I should be able to measure in whatever process you want to talk about, and it's tractable, then I can go out and have my grad students actually do the measurement, and hopefully that will be successful in the sense that they agree. But even if they don't, it tells you there's something wrong with presumably something wrong with the model. Right. And that can help to iterate the model, and that actually is meaningful.
Yeah, as someone who's really, and I think you have too, Mike, really tried to, engage with people in theory and computation, for experiments. One of the issues is that you say, okay, I'm going to study, this interface, or I'm going to do this process, that sort of thing. And so at that point, what you can do is you can engage your colleagues in theory. You can call them up and say, guess what? I'm going to start a whole series of new measurements on, on X. Right, and they go, great, we'll get, computers are spooling up right now, and we'll get all this thing going. And then, sad to say, sometimes experiments don't work, right? And, you sort of get your student or your postdoc to do it, and it doesn't work for a little while, and then you go like, oh, what the hell, that was such a dumb idea anyway, we're done, right? Meanwhile, your colleague is over there cranking away, right? And maybe something happens and maybe something doesn't. And so really the question is, can you do this in parallel? I.e., could I call up Perla or Don at the beginning of the experiment cycle, right? An example would be we were looking at alloys and CO2 reduction, right? I had, I'm sitting here at my desk, my student comes in, I say, throw in tin, throw in silver, throw in, nickel, see what happens, right? And so do I then call you up and say, oh, I'm doing these things right now, and my students are sitting there with little charts about, here we did 2%, not a much of an effect, but by the time we got to 2.5, boy, let me tell you, right? Do I get you then, or do I call you afterward and say, look, 2.5% tin, presto, best, you know, ethylene producer on the planet, right? Please tell me why. What's the right time to get you all engaged?
I think that that goes to the problem that I was trying to point out, that is how to define the model properly. And for that, we need a lot of information, as I said before. So we need the information that the steps in the process that help you to define your material in order for us to define the material that we are going to use in the model. And it's not just telling me, well, it's a nickel cobalt alloy and just work with that. And it could be, depending on the way you process, you obtain the nanoparticles or whatever, you get different reactivities, different physical properties. We all know that. So the right moment, what would be the right moment? I guess it could be somewhere in between well, when we write proposals together, we do it from the very beginning, right? Because we are thinking together about the process and saying, well, what I'm going to do this and the experimental is going to do that. But sometimes it's not, and sometimes later we diverge. We do some things, the experimentalist does other things. So, yeah, in order for the model to be realistic, it needs the experimental input. That's definite. And the best moment is the moment when we are trying to understand the results of the experiment, but you already know how you did the processing of your material.
Yeah, and to Perla's comment, I mean, she actually said this, but the question of when should theorists and experiments start to coordinate, I think the answer, unfortunately, is it depends. It depends on the problem. It depends what you're trying to do. If you're trying to discover a new composition of a material, and you know there's a huge phase space available to you, I think computation could pretty quickly from the beginning say, you know, here's some compositions which are unstable or somehow dead ends, maybe they're thermodynamic dead ends. So there's some filtering that could happen in that particular type of problem that I think would be helpful right from the beginning. It couldn't guarantee success, and that, you know, one couldn't promise that you could make the materials that were calculated or predicted to be the best, but and there are just some problems which are better probed experimentally than computationally. And I feel sad when I have to say it, but sometimes people come and ask me to do calculations and I say, you should do that. It's easier for you to do that experiment in 1 week than it is for, you know, my group to do it in 6 months.
So can I maybe follow up on, Jordy, you're muted, but maybe follow up just very briefly on this. You know, one thing that we don't do particularly well as educators is have students who can do at least reasonably easy well experiments as well as theory. So that kind of, you know, the same person would be then doing both. And, you know, I may have had a couple of students at best who've kind of tried to do this, but it's a hard thing, and it's something that we don't often encourage, and maybe something to think about going into the future.
I explicitly discourage that because I think it's, I mean, if we're talking about a PhD student, I think you need to be deep in one area and do groundbreaking work. I think it's hard to excel in multiple areas. So I think it's okay to learn, but if it's critical to learn, you know, what can be done experimentally and what can be done computationally. But
I've had one student in 50 who really was able to do both.
So,
Rebecca has a question that is related to what you're just discussing. So why don't you go ahead and put it in kind of the way that you were putting it to me, because I think this is very relevant now.
Sure. The first question. So I guess I'll give a little background. I'm a experimentalist, mostly working with electrochemistry for catalysis, and we work with experimentalists, and I've done a little computation, but what's hard to know is someone who's primarily experimental is what computations can a person do, and who does mostly experimental work, and how much do they rely on a computational collaboration based as doing it themselves? Like, how much can you do yourself if you only understand really the basics?
Basically, should an experimentalist do any computations whatsoever?
I think it depends on the level that you want to do this and whether you have a colleague who can help you or not. Honestly, I think that it's certainly possible to get VASP, for example, and hit return on VASP for a little while. But whether the results that come out are going to make any sense or are going to be, you know, rigorous enough for publication is something that probably you or your experimentalist advisor like me, for example, would not really be able to say, just in the same way that, no shade on either Perla or Don, but you know, if there was a certain experiment or that sort of thing, you know, you were going to do it in your laboratory, it's complicated to be an expert at that and also be an expert at what you do in theory. In the one case where I was successful, my student had two advisors. One was me and the other was Jeff Greeley, right? So she did experiments with me and then drove to Purdue and did calculations over there. And I didn't really feel competent to advise her in the calculations. And I think Jeff felt the same way with theory, with experiment.
How about the other way around? You know, a computational person that feels like doing some experiments. Is there a set of simple experiments that, you know, just to be cheeky, even a computational person could do, right? The same way that Rebecca's question is there any, you know, computations that even an experimentalist could do?
You gotta want it. That's the only thing to say. With everything, both in theory and experiment, you gotta want it. And so, you know, I think Mike will agree that, you know, the sad news about experiments is that they don't work, right? And so, you know, you go in, you try something, it doesn't work. What happened? There was smoke, there was, you know, thunder, there was lightning, right? Why was that? What are you going to do differently the next time? You got to want it. You know, you got to be able to do the problem solving that makes it all work. And I imagine, in fact, I know there is the same sort of thing in theory, right? You hit return and you get, you know, the lifetime of this, you know, the energy level of this thing is the energy level of the sun, right? You know, or something like that. And then there's a mistake and you got to find the problem and solve it, right?
So is the answer that there's no scope, you know? There are groups that do both, right? So
it's possible, but I think the same individual, it's harder.
But yeah, I mean, getting back to Andy's comment, I think that if you really want someone a student or anyone to be able to do this, having it, you know, good advisors in both areas is going to be absolutely essential in this case. I mean, it's the same thing if I want to do, or, you know, someone who does X-ray scattering stuff. If I want to do a Raman measurement, you know, I can do it, but I need someone who actually understands this for a sanity check on whether what I've done makes any sense.
It's a small point, but I also think it's a lot more fun to work with other people with different expertise rather than sort of collecting all knowledge in my group, be it for theory and experiment. I tell my students, you're going to have the most fun if you find another grad student who's working on experiments in a different group. You collaborate. Life will be much better with friends.
Okay, so I'd like to call on Olga, who had a question that is kind of along the lines of the dialogue between experimentalists and computational scientists. So Olga, you should be able to ask now if you unmute yourself.
Yep. So kind of related to the discussion currently going on. So going further, as Dr. Siegel pointed out, from catalyst characterization to prediction, I'm really wondering what sort of information do experimentalists find most valuable? For example, a concern with machine learning-based catalyst discovery is that it does not necessarily find catalysts that are of reasonable structure or easy to synthesize. So therefore, experimentalists tend to sometimes be skeptical of the predictions and some of the catalysts that we design. So what do you think are the prospects, both current and forthcoming, that would help bypass this issue? And how can computationalists ensure that the catalysts that they predict with more newer approaches such as machine learning are reasonable?
What's the answer? Go ahead.
I don't know if this was directed to me, but I mean, I would always start with the concept of thermodynamic stability. These are things which can't, I mean, we can calculate whether something is stable or marginally unstable or very unstable. And, you know, there are some difficulties associated with when you have surfaces and defects, but you know, if the bulk material is very unstable, I would not recommend that as a starting point. Now, of course, synthesis is something which has already been mentioned. And so, you know, I could imagine a theorist could make a prediction about a material which based on thermodynamics should exist. But whether that could be synthesized is an entirely different question and often much more difficult to predict. So I think if you think something can exist based on thermodynamics, you still have no guarantee that it can be made today. Maybe you can say, well, you guys just aren't smart enough, and 20 years from now, your synthetic techniques will be so much better. So we'll check back in the future.
Of course, the carbon-based anode of a lithium-ion battery is thermodynamically unstable.
Yeah.
Right. So that was obviously a poor research direction. Yep.
And so you can't take the human, well, so the story of that discovery, right, relies upon, I guess, the SEI and
right.
human intuition.
Right.
Yeah.
Well, but this goes a little bit, Andy, to what you were saying in the beginning about, you know, can you predict something that I can really bother making, right? So, you know, how do you bypass that? And yeah, how do you go about it?
Yeah, I mean, I think the things that we make usually come from our intuition, right? At least that's what happens in my laboratory. I think about, and you know, simple things, acid bases, hard soft acid bases, or some electronegativity things, very simple arguments that have little or no sophistication in back of them. In fact, are usually wrong. Okay, and it would be nice to have some sort of, you know, wingman or wing person who would say, oh, here, if you just, you know, take that concept a little bit further, right, here's some place you could go, you know, that might be better. And that would be what I would be looking for, quite honestly. And it may be that I'm just not talking to the right people, or, you know, not up to date, something like that. But that's really what I think would be really useful, to take these simple concepts, hard, soft acid bases, things like that, and move them a little bit further.
And the other point is that predictions are not, especially when we refer to machine learning or high throughput predictions, are not something that will, you know, take place by any magic or anything like that. I mean, it has to be science into that, right? And it has to be, we have to guide the computer in order to train the computer properly in order to make the predictions. If the information or the objectives that we give to make those predictions are not the correct ones, it's not going to happen. I mean, it's not going to be a good prediction. So what I would do in that case is to look and see what went wrong. because in the prediction could have participated both experimentalists and they really have to participate, experiments and theoreticians. So so the definition of the problem becomes better.
On this, so we're discussing a lot about that dialogue between computations and experiment, and there's yet another question that touches on that angle from a slightly different perspective. So I'm going to bring Chi Sheng. Hopefully I'm pronouncing the name correctly. Go ahead.
Thanks, Jordi. Can you hear me?
Yes.
So this is Chi Sheng Wu, a postdoc at Michigan State University. I'm a modelist working on atomic simulation with electrolyte, anode materials, and the solid electrolyte interface. My question is that what should I do to improve the efficiency collaborating with the experimentalist? I find that there is often a gap between us in understanding a specific problem. And as Andrew pointed out, experimentalists tend to expect results that are more close and comparable to the experimental measurements, but it really takes time to think how to connect the theory and experiment. Sometimes I need to spend much time dealing with my own theoretical and modern details, and thus the overall progress of the collaborative project could be delayed. So yeah, so I've been struggling. I'm having now a collaboration with experiment. Do you have any advice on improvement of this? Thank you.
So I'm gonna chime in just to rephrase that a little bit in slightly more controversial terms, connecting to what Jeff was saying before, which is this notion that experimentalists tend to have that they'll walk in with a piece of paper with the result and say, give me the model that matches this so I can put it in my paper, because if I put it in my paper, I get a higher impact. And your computer can do this very quickly, right? So, you can do this by tomorrow, right?
Right.
So, there seems to be a misconception there. And so, what needs to happen so that disconnect kind of goes away? Because that Jeff was getting to that too.
So I would say one bit of advice is be honest. So I mentioned earlier that there are some things which are hard to do computationally, and I don't feel like we should be wasting people's time. If you can't do the calculation and it's better done experimentally, just tell your friends that, this isn't a good problem for us to collaborate on, and explain to them why. The other thing that's really critical is, I get the impression that some people think that computation is, you download the code, you press enter a few times and you get a result. I would say the most time-consuming and important part of running a simulation is generating the model. And Perla mentioned this, what goes into the model, how do you construct it, how do you run the calculation in a way that you get meaningful data out is super important. And that's one of the reasons why I'm also a bit skeptical about people trying to excel both in computation and in experiment, because it takes some time and some wisdom to learn how to generate the right thing to simulate. And you need to make sure that it's apples to apples, that you're simulating the same thing that's being probed experimentally. And be prepared that in some cases it just might not be possible. There might be complications in the experiment. There might be phenomena that are beyond the length, the time scale, or the complexity that your simple model can capture. And it's okay to acknowledge that.
So, getting back to this question, one thing that I would specifically suggest is that you try to engage your experimental colleague early and often. So when you're thinking about the problem you're trying to go after, it could be a collective discussion. And that can help to avoid, I think, the problem that Annie mentioned, which is I come back with some data, the theorists explain it, I stick the figure in the paper, even if it doesn't quite agree. So if you start that discussion early on in the problem definition, then you'll have a better likelihood of actually being able to come up with a simulation that's tractable and meaningful, as well as an experiment that's tractable and meaningful.
Yeah, I think just in the same way that when we run an experiment, it's good to ask the question, what do you expect the outcome from this experiment to be? Or if everything worked well, what would be the outcome? I think it's the same way with a collaboration or with a computation. If everything works perfectly, what's going to be the outcome? And is that something that you and your collaborator actually agree on? And I agree with Mike, certainly having communication early and often about exactly what you can do, what they can do, and how they might come together, I think it's very useful.
So it turns out that one of the students, or one of the attendees, I don't know if he's a student or postdoc, had a suggestion on perhaps how this could be made to work. So Siddharth, why don't you kind of, put on the table the idea that you were throwing?
Hi, can everyone hear me?
Yes.
Yeah, so I'm Siddharth. I'm a PhD student in Jeff Greeley's group at Purdue. And so everybody is trying to make this point. So I sort of want to probe this point of experimentalists and theorists talking with each other a little bit further. And I want to ask a question. And what I have seen a lot of times happen is that as a theorist, I really don't completely understand what the experimental result is trying to tell me. So I don't know what is the certainty of the conclusion, how they came to that conclusion, and really what is the level that I can say that, okay, this happened, because I'm not naturally trained in it. And I'm pretty sure the same thing happens the other way around, where sometimes experimentalists read our papers and they don't, at least I feel so, and people can correct me if I'm wrong, that it's possible that experimentalists don't exactly understand what are the assumptions of our model, what are the limitations of it, what are we saying by default when we report something, where can it break down? So is there some thought on having some education on both the fronts, where there is some one-on-one on the experimentalist trying to explain when they do a certain measurement, whether it's X-ray absorption spectroscopy or any kind of Raman of like what they see, how they come to that conclusion, and the other way around from theorists when we, let's say, report like some descriptor, what that means, what is the underlying assumption in the model, and what do people think about this?
So again, to paraphrase this would be like, the anathema of anathemas, which is that computationalists and experimentalists spend time together, socially almost, right? So what do you, what do you envision this, how could this be made to work?
Well, I think, again, it just has to do with the communication aspect, right? And when you're collaborating with somebody. So I think this is an excellent point. Certainly, it's possible to say, oh, the experiment shows something, and in fact, it doesn't, right? Or you just think it does, and you don't really know, or you just wish it did, but you don't really know, right? I see Jordy smiling and Mike's smiling because we all know, right? So, so then having, real honest communication about what it is your experiment actually is saying, what the conditions are. And we're all supposedly chemists and physicists, and so we're all supposedly working in the same physical reality in concept. So it should be, you should be able to understand some of what that is. Here's a spectrum, here's a peak, that sort of thing. And likewise, I think an experimentalist certainly understand that if you use a certain basis set or something like that, that you might get one result, and if you use another basis set, you might get another result, or things like that. I think being very honest about what it is and having communication is very important.
So do I hear that perhaps the message that you want to give is not so much that people need to learn how to do both? This is a question that came up earlier, right? They were asking, well, maybe a computationalist should, the ideal would be that somebody does both computations and experiments, and you push back against that idea because it's hard to be good at both. But perhaps there's room for a computational person to understand experiments better, even if they cannot run them, and experimentalists to understand computations better and what they can or cannot do, even if they cannot run them directly, which takes a different skill. Is that what I'm hearing? Anybody want to comment?
I think part of this can just come down to asking challenging questions on both sides, right? And at some level, you need to learn what those are. But you know, just by starting by questioning either the computation or experiment, how confident are you? So what about this interpretation? Things like that can kind of start that dialogue. That reminds me, I once heard a very well regarded theorist make the statement, it's an experiment, it must be correct.
I thought it was the other way around.
And for those of us who do experiments, I just reacted with horror at this explanation because all experiments are not right. We make mistakes. So it's important to realize this, and you know, my theory colleagues, I'm sure, would be willing to make the same comments that all computations are not correct. You just look in the literature. Some of them disagree, so they can't be right.
I think there's an opportunity to re-examine our graduate curricula because, at least in Michigan, you know, we don't place any requirements on our graduate students that they must take both, you know, a course on rudimentary computation and a rudimentary course on experiments, whatever that would be. And so people go through their PhDs, they pick one track, they learn one thing in depth, and they're totally clueless about what, you know, their non-theorist or non-experimental colleagues do.
You know, very interesting that you raised that issue of curriculum, because I have saved a question that I really wanted to put on the table that has to do with education that came up this morning. And so Michael is going to ask it to you too, to get your takes, because you're also more diverse in terms of the departments that you represented this morning. So Michael, go ahead.
Okay, thanks again. My name's Mike Gerhardt. I'm a postdoc at Lawrence Berkeley National Lab. And so the question I've been asking is, how can we improve the teaching of electrochemistry since it spans such broad and interdisciplinary problems? The way I've been phrasing it is, should it be kind of structured into its own department or squeezed into one of the existing ones? But how else would you try to improve the teaching of electrochemistry today?
Well, I mean, you know, I think in my department, a chemistry department, we have a graduate course on electrochemistry. And I think we've had a series of, you know, and have right now a very good instructor in Joaquin. And so I think that part's okay in terms of, but what I do see, and again, this was touched on a little bit this morning, is that you have people who want to get into a field, let's say batteries or catalysis, electrocatalysis of some kind or another. The kind of ability to have a book where you can sit down and read it and you know, sort of understand what's going on is limited because those books are limited. And that's a problem.
That's funny because the last panel said the same thing. We need a new book.
Yeah, no, I agree completely. No, we all agree. And even I think I can share that the second volume of Barden Faulkner was trying to do something pedagogically that may not have worked as well as the authors hoped.
So is there going to be a third edition?
I understand that there is, but I don't have any direct knowledge of that.
Well, Henry, right?
With Henry, right? That's my understanding.
Tito mentioned that this morning, I think.
Yes.
Should there be a new Newman book too?
I know less about that one, but I know less about that one.
Yeah. No, I mean, talking about the, I was talking to, you know, Perla and Don, talking from the engineering side. Yeah, so Perla, go ahead.
Yeah, I was going to say that Newman is electrochemical engineering, whereas the other ones are most focusing on the electrochemical science, if you want.
So is there opportunities for better education on electrochemical engineering, basically? Is that, you know, should it be its own department finally, or?
Yeah, yes, definitely. My department doesn't have a course on electrochemistry. And my department is chemical engineering. We don't have a class on electrochemistry. I don't know if it existed at some point, but never since I'm there. But I think that, yeah, it would be nice to have like a new approach to electrochemistry, going from the basics and going up, right? So, but yeah, it will require maybe a new textbook, or not necessarily. One can do well developing a class without the textbooks as well, taking from materials from several existing textbooks.
Yeah, I mean, I think that the as topics in electrochemistry have changed to, you know, batteries, the associated solid state issues, which are, you know, dramatic these days, and to issues in electrocatalysis. I think perhaps textbooks haven't quite kept up with all of that.
Anybody wants to add anything else to that? Mike, did that cover, Mike, the questioner, did that cover your question?
Yeah, I think it's interesting just to hear the different perspectives on it. So thank you.
Yeah, if you're there tomorrow, I'll have you ask those people as well, because they have very different perspectives. Yeah. Okay, so we are at 2:30, and this has been a very robust discussion. So I'm sure that both the attendees and the panelists need a bit of a break. So I think we're going to leave it there. This also ends the live stream. I wanted to thank Mike, Andy, Perla, and Don, in the order that I see in my screen, for being so generous with your time and spending 90 minutes sharing your thoughts, for being so candid as well. It was very interesting to see that it wasn't, you know, all experimentalists bashing the theorists and the theorists bashing the experimentalists, which is what I was trying to get to, but I didn't succeed. But thank you for your time. Attendees, thank you for being there. There's 2 more panels tomorrow. Panelists, if you want to join for those, then let us know and we'll give you the links. There are different links to this one. With that, I'll conclude this panel and I will see you all tomorrow. Have a good evening.
Thank you very much.
Thanks, Jordy. Thanks a lot, Jordy.
Thank you.
Bye-bye.
Bye-bye.